Okay, now the next topic we looked at was differentiation and derivatives. So we started with the definition of derivatives. We said that let f of x be a function. We say that f of x is differentiable. Is differentiable at x equals a if limit f of x minus f of a over x minus a as x approaches to a, which is same as limit f of a plus h minus f of a over h as h approaches to 0 exists. If these limits exist, this is one limit. It can be written as this expression or this expression. These two expressions are equivalent. So if this limit exists, then we say that the function is differentiable. And in this case, the value of this limit is denoted by f prime of a. So f prime of a means this limit here. And if this limit does not exist, of course, we say the function is not differentiable at the point a. So for example, let's say f of x equals x squared plus 2. Find f prime of 3 using and the limit definition of derivatives. So f prime of 3, we know that its limit f of x minus f of 3 over x minus 3, x approaches to 3. And this one, we can write it as limit x squared plus 2 minus 3 divided by x minus 3, x approaches to 3, which can be written as limit x squared. So f of 3 is 11, not 3. Minus f of 3. F of 3 is 9 plus 2, which is 11. So x squared minus 9 over x minus 3, x approaches to 3. And this is limit x minus 3 times x plus 3 divided by x minus 3, x approaches to 3. Now this cancels with this, and limit x plus 3, x approaches to 3 is 3 plus 3, which is 6. So that means f prime of 3 exists and is equal to 6. Now, one fact is that if a function is discontinuous at a, at x equals a, then f of x is not differentiable at x equals a. However, note that if f of x is continuous at x equals a, then f of x may or may not be differentiable at x equals a. So the function must be continuous in order to be differentiable. This means if it's not continuous, for sure it's not differentiable. But if it is continuous, still we don't know. We don't know whether it's differentiable or no, depends on the function. When I say we don't know, I mean we don't know in general, but for a specific example, if the function is given, then of course we can find out whether it's differentiable or not. So graphically, you know, if a function has sharp points, for example, like absolute value x at 0 is continuous at x equals 0, but not differentiable at this point because it has a sharp point. If it has a sharp point, it's not differentiable, but this function is continuous at 0. So you can check this mathematically, use the definition of continuity and use the definition of differentiability to show that the function is continuous at 0, but not differentiable at this point. Okay, so for example, let's say f of x equals, let's say 2x plus 1 if x is bigger than or equal to 2, and minus x if x is less than 2 is not differentiable at x equals 2 since it is discontinuous at x equals 2. I leave this for you to check this fact that it's discontinuous at 2, and then you can conclude that you can say that by a theorem, we know that if a function is discontinuous, then it must be non-differentiable at that point. So this function is not differentiable because it's discontinuous. So just check that it's discontinuous and then mention the theorem and then conclude that it must be non-differentiable at x equals 2. Now, another fact is that if f of x is differentiable at x equals a, then f prime of a represents the slope of tangent line at x equals a. It also represents the rate of change, or the instantaneous rate of change, instantaneous rate of change of f of x at x equals a. So for example, in example above, if we had f of x equals x squared plus 2, and if we want to find the equation of tangent line, at x equals 2, well, we know that f prime at x equals 3, so we found a derivative at 3. So equation of tangent line would be y minus f of 3 equals f prime of 3 times x minus 3, because you know the slope, the equation of the line is y minus y naught equals m times x minus x naught. Now y naught is f of 3, x naught is 3, and slope is f prime of 3. So then that gives y minus 11 equals 6 times x minus 3. And that will give me y equals 6x minus 18 plus 11. So that's going to be minus 7. So y equals 6x minus 7 will be the equation of tangent line at x equals 3. It can be also written as instantaneous rate of change, for f of x at x equals 3. We also looked at the derivative rules. Derivative rules. You know, for example, with we have, let's say if u equals f of x, set u equals f of x, v equals g of x. Then we can say that u plus v derivative is u prime plus v prime. Cu derivative is cu prime. U times v derivative is u prime v plus u v prime. U over v derivative is u prime v minus u v prime divided by v squared. F of u derivative is u prime times f prime of u. This is called chain rule. So for example, let's say if you want to find x squared plus 1 to power 6 derivative, so this is going to be derivative of u to power 6. U to power 6 derivative, chain rule says that if you have a function of u, to find the derivative, just the usual derivative, but times u prime. So x to power 6 derivative is 6x to power 5. This was a power rule. I could also mention this here. X to power n derivative is nx to power n minus 1. It's called power rule. So u to power 6, x to power 6 derivative is 6x to power 5. So u to power 6 derivative is 6u to power 5. But then I have to multiply it with u prime. So its chain rule says the usual derivative, f prime of u, then times u prime. So 6u to power 5 times u prime is the derivative of u to power 6. So here will be 6x squared plus 1 derivative times x squared plus 1 to power 5, which is going to be 12x times x squared plus 1 to power 5. Other derivative rules that we have seen before, you know, for example, e to power x derivative is e to power x itself. So that means e to power u derivative is u prime times e to power u. Or ln x, for example, and ln x derivative is 1 over x. That means ln u derivative is u prime over u. Sine x derivative is cos x, which means sine u derivative is u prime times cos u. Cos x derivative is minus sine x, and that means cos u derivative is minus u prime times sine u. Tan x derivative, secant squared x, that means tan u derivative, u prime times secant squared u. Cot x derivative minus cosecant squared x. So that means cot u derivative minus u prime times cosecant squared u. And so these are some basic derivative rules. Then we also saw about implicit differentiation. Implicit differentiation we saw that, you know, if you have, let's say, f of x and y equals 0, so this is called an implicit equation. Implicit equation. Then we can differentiate both sides to find basically dy to dx. Differentiate both sides. using derivative rules. Derivative rules, and have in mind or keep in mind that derivative of terms and containing y must be computed using the chain rule. So for example, if let's say you have sine y equals x times e to power y, and let's say you want to find a y prime or dy to dx. So if I differentiate both sides here, what is derivative of sine y? Sine y derivative, because y is a function of x, right? So it's like sine u derivative. Sine u derivative we just mentioned a few minutes ago, it's cos u times u prime. So similarly, sine y derivative is cos y times y prime. So y prime times cos y equals, now for the other side, derivative of a product of two functions, I have to use product rule. So first derivative times second plus second derivative times first. So first derivative is 1 times e to power y plus x y prime e to power y. Derivative of x is 1. Derivative of e to power y is e to power y times y prime. And then if you want to find y prime, I can isolate for y prime times cos y minus x e to power y equals e to power y, right? I'm taking this term to the other side and then factor y prime out. So isolating for y prime, and then I can solve for y prime. Just divide both sides by the coefficient of y prime, which is cos y minus x e to power y. So that means y prime equals dy to dx equals e to power y divided by cos y minus x e to power y. Okay, we also saw about the concept of related rates. So related rates, let's say we have two functions, y and x. Let's say y equals f of x. So normally x is an independent variable, y is a dependent variable, a function of x. But when we talk about in the context of related rates, x itself is also dependent variable, and y, of course, is also dependent variable. What is independent variable? A third variable, let's say t or time. So suppose that x is equal to x of t, and y will be equal to y of t. So basically t will be the independent variable, and x and y dependent variables. Then we can say that the rate of change of x will be related to, that's why it's called related rates, because rate of change of x will be related to rate of change of y. Rate of change of y via which relation? So see if we have y equals f of x, if I differentiate both sides respect to t, then left-hand side will be dy to dt or I can call it, let's say I can call it y prime, let's say, leave it as y prime. And right-hand side derivative of f of x itself is a function of t. So you have to use chain rule, like f of u. What would be f of u? U prime times f prime of u. So similarly here, f of x derivative would be x prime times f prime of x. Or in Laplace notation, you can write it as dy to dt equals dx to dt times f prime of x. So for example, let's say if you have a balloon, if a balloon, or let me say if the radius of a balloon is increasing at the rate of, let's say, 2 centimeters per second, find the rate at which the volume is increasing. So the rate of change of radius is given, the rate of change of volume is being asked. So we have to, it's a related rate question because we want to know how we can relate the rate of change of radius with rate of change of volume. Once we know their relation or connection, and one of them is given, we can find the other one. So first you need to find the relation between the two quantities themselves before thinking about rate of changes. So first find the connection between the quantities that are mentioned in the question. Then we can differentiate both sides to find the connection between their rate of change. So right now, we want to know the connection between radius and volume of a balloon, which means a sphere. Spherical balloon, just to emphasize it. Spherical. What is the connection between radius and volume of a sphere? Well, we know that V is equal to 4/3 pi r cubed. Now, if I differentiate both sides, so this is the connection, still no derivatives involved and no rates of change. But once I differentiate both sides, then I can say that V prime equals a derivative of 4/3 pi r cubed. Well, 4/3 pi is just a constant. Derivative of r cubed is 3r squared times r prime. Why times r prime? Because r itself is assumed to be a function of t. T is the independent variable, and v and r are both dependent variables. They are both like u. So for both of them, I have to use the chain rule. So v prime equals 4/3 pi r times 3r squared times r prime. Or in Leibniz notation, I can write dv to dt equals 3 cancels with 3, so 4 pi r squared dr to dt. So we also need to know the value of r to find the rate at which the volume is increasing when the radius is 3 centimeters, let's say. So the value of r must be also given. So dv, so if r equals 3 centimeters and dr to dt is equal to 2 centimeters per second, then we can say dv to dt is equal to 4 pi times 3 squared times 2, and this is 8 times 9, 72 pi centimeter cube per second. Okay, so this is how we can find the rate of change of volume in this case. All right, now then we looked at some applications of derivatives. And we looked at mean value theorem, or MVT, and Rolle's theorem. So MVT basically tells us that if f of x is a continuous function, on the interval, closed interval a and b, and differentiable on open interval a and b, then there exists C between A and B such that f prime of C is equal to f of B minus f of A over B minus A. So if I want to explain this graphically, we have a function which is differentiable and continuous, let's say like this. And the right-hand side, f of B minus f of A over B minus A, is the slope of secant line connecting the endpoints of the graph, of the curve, basically. Let's say this is A and f of A, and this is B and f of B. And this is the line, secant line connecting these 2 points. And then there must be a line, a tangent line, which is parallel to this. So f prime of C means slope of tangent line at C. So slope of tangent line at C must be equal to slope of secant line. Slope of two lines being equal means that those two lines must be parallel. So that means the tangent line at C must be parallel to secant line. So the theorem guarantees that at least one tangent line is parallel to the secant line, as long as the function is continuous on the closed interval, differentiable on the open interval. So here, basically in this picture, so C could be somewhere like here, these two lines are parallel. Therefore, if I call this one, let's say L, L1 and L2, ML1 equals ML2. Now, ML2 here is f prime of C, and ML1, slope of L1, is f of B minus f of A over B minus A. Okay, now Rolle's theorem says that with f of x described above, in MVT, as in MVT, if f of A equals f of B, then there exists C between A and B such that f prime of C is equal to 0. Well, look at MVT. If f of A equals f of B, then right-hand side becomes 0, and f prime of C must be 0 for at least one C between A and B. So I also explained that some people ask here that, well, Rolle's theorem seems like an immediate conclusion or a trivial conclusion of MVT. We just need to set f of A equals f of B. And then right-hand side, of course, will be 0. So why are we giving this a different name, or why is it important if it's just an immediate conclusion of MVT? Well, I explained that MVT itself will be proved using Rolle's theorem. So the order is, first, Rolle's theorem will be proved. Well, we didn't prove it actually in this course, but if you are interested in the proof, you can take an analysis course. But basically, the order is Rolle's theorem first is proved, and then MVT can be proved using Rolle's theorem. And f prime of c equals 0 means you have a horizontal tangent line, because if a slope is 0, that means that line is horizontal, and f prime of c is slope of tangent line. So that means at least one tangent line becomes horizontal if f of a equals f of b. So we can look at, for example, this picture here. F of a and f of b are equal, and we have a horizontal tangent line as predicted by Rolle's theorem. Okay, so we also saw some applications of MVT. For example, we saw how to prove in an inequality, so proving inequalities. And other applications. Maybe the most important application was the criteria for increasing, decreasing functions. Decreasing functions, and also a constant difference theorem. So basically, we saw that if, let's say, f of x is, let me write down here as an assumption. So suppose that f of x is continuous on closed interval a and b, and differentiable on open interval a and b. Now, if f prime of x is positive on a and b, then f of x is increasing on this interval. If f prime of x is negative on a and b, then f of x is decreasing on this interval. And finally, if f prime of x equals 0 on this interval, then f of x is a constant function on this interval. Okay, so for example, if you look at f of x equals 3x squared minus x. So we want to know where the function is increasing or decreasing. Well, we can find f prime of x. What is f prime of x? F prime of x is 6x minus 1. So if we put it equal to 0, then that gives x equals 1 over 6. Then we can use a sign chart. Sign chart, in sign chart, we can locate the zeros of f prime. There's only one of them here, 1 over 6. And then first row, we determine the sign of f prime. Second row, basically second row sign of f prime. Third row sign f itself, not sign of f, whether f is increasing or decreasing. And f prime is 0 at 1 over 6. Before 1 over 6, we can use a test point. For example, x equals 0 is less than 1 over 6, right? So we can use it as test point. Then f prime of 0 will be 6 times 0 minus 1, which is less than 0. So negative here, positive here. And then f means it's decreasing here and increasing here. And then 1/6 will be called local mean. So we also defined basically local extremum. So x equals a is called a local mean for f of x if f f of x is less than equal to, sorry, bigger than equal to f of a for every x in I, where I is an interval, is an open interval containing x equals a. So first of all, if x equals a wants to be a local minimum for f, first of all, f must be defined on both sides of a. So f must be defined on an open interval containing a. And so open interval means like the neighborhood of a little bit from left and a little bit from right of a. And on an interval which consists of points a little bit less than a, and points a little bit less than a, and points a little bit bigger than a, f of a must be the smallest one among the points of such interval. Okay, so here, for example, look at this. So this is, let's say, x equals 2. Let's say this is x equals 5. And let's say this is x equals 7. So here x equals 2 is a local minimum. Why? Because I can consider an open interval containing this point where f of 2, so this could be my interval I, and this is f of 2, and f of 2 is less than equal to f of x for every x in I. Among all the points in the interval I, f of 2 is the smallest output. But what about 7? So similarly, x equals 5 is the local maximum. So we provide the definition of local minimum. Local maximum is also similar. Let me write here, similarly, local max can be defined. You just need to have f of x less than equal to f of a for every x in I for local max. But the rest of conditions are the same. So x equals 5 local max and x equals 7. Neither local mean nor local max. Why? Because x equals 7 is an endpoint. X equals 7 is an endpoint, and the function is not defined on both sides of that. So if you want to have local mean and or max, first of all, the function must be defined on both sides of the number, and therefore an open interval containing the point will be included in the domain of the function. And then on that interval, if f of a is the smallest one, then you have local mean. If f of a is the biggest one, then you have local max. Now, some facts about local extremum facts. if f of x is or has a local extremum at x equals a, then x equals a must be a critical point for f of x, meaning that f prime of a does not exist, or f prime of a equals 0. So critical point means a point where derivative does not exist at that point or derivative is 0. Now, if f of x has a local extremum, then it must be x equals a must be a critical point. So that means if you want to find the local extremum, local mean and local max, the potential candidates would be critical points. Once you find the critical points, each of those points could be potentially a local extremum, but there is no guarantee. It's possible that a point is a critical point and is neither local mean nor local max. And the example is y equals x cubed. Y equals x cubed at x equals 0 has neither local mean nor local max, but x equals 0 is a critical point for x cubed. Okay, so if it's a critical point, then there's no guarantee, maybe neither local mean nor local max, but every local mean or local max must be chosen, will be chosen from the list of critical points. So to find local mean and local max, first you have to find the critical points and then look at every critical point, each critical point. Each critical point could be local mean, could be local max, could be neither. How can we find out? We can either use the first derivative test or second derivative test. So to find out whether whether a critical point is a local extremum, use first derivative test or second derivative test. So first derivative test, I basically showed here. See if a function is decreasing and then increasing. So it should go down and then go up. So then you have a local mean. But if it's increasing and then decreasing, going up and then down, then you have local max. But then if it's decreasing and also decreasing or increasing and increasing, then you have neither local mean or local max. So this is how you use the first derivative test. And what about the second derivative test? Second derivative test says that, if let's say x equals a is a critical point for f of x, and if f double prime of a is positive, then we can say that x equals a is a local minimum. Similarly, if f double prime of a is negative, then we can say that x equals a is a local maximum. for f of x. So for example, in example above, x equals 1/6 was critical point. And how much is f double prime of 1/6? Let's look at the example. F of x was 3x squared minus x. So first derivative is 6x minus 1. Second derivative means derivative of first derivative. That's going to be 6. At 1/6 is still 6 because it's a constant function. So f double prime of 1/6 is 6, which is positive. So that means x equals 1/6 must be local minimum using second derivative test. But using first derivative test, we also reached to the same conclusion that it must be a local minimum. Okay. So second derivatives can be also applied. So second derivative can be used to determine local mean and local max. It can be also used to determine concavity. So concavity, we define concavity, we define concave up and concave down. Concave up, concave down. So definition itself is not related to derivative. Definition of concavity is not related to derivative. But one criteria that we can say, if a function is twice differentiable, then we can look at the sign of second derivative. And we can say that if f double prime of x is positive on some interval, let's say a and b, then we can say that f of x is concave upward on this interval. And similarly, if f double prime of x is negative, again on a and b, then f of x is concave downward on this interval. So there is a connection between second derivative and sign of second derivative with concavity. So for example, again, in example above, we saw that f double prime of x is 6 for every x between minus infinity to infinity. So that means f of x is concave upward. On this interval, minus infinity to infinity. And we also gave definition of inflection point. Inflection points, a point where concavity changes at that point. So from up to down, or from down to up. So for example, this function here has no inflection point because it's always concave up, right? So the concavity does not change at any point. It's always concave up. So then this function has no inflection points. Okay, we also saw about the concept of absolute max and mean. So this one we defined, and that, you know, x equals, let's say a is absolute max of f of x if f of x is less than equal to f of a for every x in domain of f. for every x in domain of f, you have f of x less than equal to f of a, then we say x equals a is absolute max. Similarly, we can define absolute mean. Similarly, absolute mean can be defined okay. So how can we find absolute max and mean? First of all, which functions are guaranteed to have absolute max and mean? So that one we sign extreme value theorem. Extreme value theorem said that if f of x is continuous on a closed finite interval, closed finite interval a and b, then f of x takes its absolute max and takes its absolute mean on this interval. Because not every function takes absolute max and mean. For example, f of x equals x on minus infinity to infinity doesn't have absolute max or mean, because as x goes to infinity, f of x goes to infinity, so no absolute max. And as x goes to minus infinity, f of x goes to minus infinity, so no absolute mean either. But if a function is continuous on a closed finite interval, then it must take its absolute max and must take its absolute mean. Okay. And then, so this is about existence of absolute max and mean and how to find it. How to find absolute max and mean, max or mean. We said that, we have to compare, we have to find the candidates first. Candidates for absolute max and mean are endpoints and also critical points. And then we have to compare the outputs corresponding to 1 and 2 above. So you will find some inputs here in 1 and 2. Each of those inputs have one output. So then you will have a list of outputs corresponding to 1 and 2 above. And then you will have a list of outputs. And then once you compare them, you can decide which one is the largest. The largest output will give you the absolute max. The smallest output will give you the absolute mean. So we did some examples here, and we also did some applications. So for example, one of the applications, simple applications, of absolute max or mean. Basically, we also call it optimization. Optimization means you want to maximize or minimize a quantity. How can we do it? So for example, we said that find the dimensions of a rectangle which has the perimeter 10 and has the largest possible area. So in this type of problem, optimization problems, we said you have to first assign some letters to the quantities in the question. So here we want to find the dimensions of rectangles. So there are two quantities. We want to find length and width. So let's say we call them X and Y. X and Y, width and length of the rectangle. And then we said that then you have to express the quantity that you want to maximize or minimize in terms of one variable only. Why one variable only? Because this is a one variable calculus. We only know how to maximize or minimize a function of one variable. Later in calculus 3, once you learn how to maximize or minimize a function of two variables, then you don't have to write in terms of one variable in that course. But here we have to write in terms of one variable only. So write area, which is the quantity we want to maximize, in terms of one variable only. So area is equal to X times Y. And what is Y? Y is, because we know that the total perimeter must be 10. Total perimeter is 2x plus 2y, so that must be 10. So that means x plus y must be 5, and y is equal to 5 minus x. So x times 5 minus x. And what is the domain of this function? With domain 0 to 5, right? Because x, of course, should be non-negative. It's side of a rectangle, and it cannot be bigger than 5 because x plus y must be 5. So addition of x and y is 5. So none of them can be bigger than 5, because if one of them is bigger than 5, then something bigger than 5 plus a non-negative number remains bigger than 5. Cannot be equal to 5 anymore. So then you have to maximize or minimize, basically want to maximize this function. And then it's a continuous function defined on a closed finite interval. So we can list the candidates. Which are the endpoints. And that means x equals 0, x equals 5. And what are the outputs corresponding to these inputs? With outputs, a of 0 equals 0 and a of 5 equals 0. And what about critical points? For critical points, I need to differentiate respect to x. So I can use product rule. Derivative of first function is 5 minus 1 times 5 minus x. Derivative of x is 1. And then derivative of 5 minus x is minus 1. So minus x equals 0. That means 5 minus 2x equals 0. X equals 5 over 2. So a of 5 over 2 will be 5 over 2 times 5 minus 5 over 2. So that's 5 over 2 the whole squared. Now if I compare the outputs that I have here, 0, 0, 5 over 2 the whole squared. Which one is the largest one? Obviously this one is the largest one. And this means this gives me the absolute max. Absolute max would be the corresponding input. This is the output, the corresponding input. X equals 5 over 2. So x is 5 over 2. And what is the value of y? Because remember, the question is asking about dimensions of rectangle. So dimensions means finding x and y, width and length. So x is 5 over 2, and that means y is equal to 5 minus 5 over 2, which is 5 over 2 as well. So that means I have a square. That's to maximize the area of rectangle must be a square. A square with side x equals 5/2. Width and length of the rectangle are both equal. They're both equal to 5/2. That means our rectangle must be a square. Okay. So we also explained about maximizing or minimizing on some interval other than closed finite, for example, infinite interval or open intervals. We saw a theorem, because maximizing or minimizing function in that case is not as straightforward, because maybe the absolute max or absolute mean may not exist in that case. But we saw a theorem that said if the function is continuous and it has exactly one local extremum overall, if overall has exactly one local extremum, then if that local extremum is a local mean, that local mean must be absolute mean. If that local extremum is local max, that local max must be absolute max. But if it has more than one local extremum, then we cannot apply this theorem and we can apply another method. So we saw some examples of this theorem that the function has exactly one local extremum. We saw some examples in the section of finding absolute max and mean. We also saw some examples in the section of applications and optimization. In some optimization problems, the domain was not closed finite, and we wanted to find this absolute max or absolute mean. So although the domain was not closed and finite, we could still apply this theorem that I just mentioned, as long as the function had exactly one local extremum. If that local extremum is local mean, then it must be absolute mean. And if it's local max, it must be absolute max. We also saw about Newton's theorem, or Newton's method. Newton's method we saw that this is a method to estimate the roots of a differentiable function. So in this method, we have to start with an initial estimation. Let's say x1 is our initial estimation. Then we can find x2. We have a formula called Newton's method formula, which says xn plus 1 equals xn minus f of xn divided by f prime of xn. So if you use this formula, then we have x2 equals x1 minus f of x1 over f prime of x1. And once you find x2, x3 will be x2 minus f of x2 over f prime of x2, and so on. So you have to start with an initial estimation. That initial estimation sometimes given the question, or sometimes you can find it using a IVT, because in IVT, remember we said if f of A times f of B is negative, then the function must have a root between A and B. So let's say f of 1 times f of 2 is negative. That means the function must have a root between 1 and 2. Let's say, for example, we could use the midpoint, which is 3/2, 1.5, as the initial estimation. So the root doesn't have to be in the middle, but we can use the midpoint as an initial estimation, and then improve the accuracy by using this formula. Once we have x1, we can find x2, x3. So x2 is an improvement to x1, x2 is closer to the actual root, to the exact root compared to x1. x3 is closer to x2 to the actual root. x4 is an improvement for x3, and so on. So when should we stop? So for example, let's say if the question says estimate up to 3 decimals. So we continue x1, then x2, x3, x4. Once we see that 2 consecutive xi's are the same up to 3 decimals. Let's say both of them up to 3 decimals are 0.123. 2 of xi's. Then that means the root up to 3 decimal is 0.123. Let's say, for example, x8 and x9, both of them up to 3 decimals are 0.123. That means the root that we are trying to find up to 3 decimals is 0.123. Okay, we also mentioned that Newton's method cannot be applied or does not converge the actual root in some rare cases. But we said that we don't want to focus on that in this course. In a higher level course, you can learn about the cases where Newton's method stops working. Okay, another topic, important topic that we covered was, sketching the graph of a function. We explained the steps. If you remember, the steps was, first you have to find the domain, and then find x and y intercept if possible. And you also need to find the asymptotes, vertical asymptote, horizontal asymptotes, and oblique asymptotes. In some cases, we have oblique asymptotes. If you remember, in particular, if you have a rational function and degree of top is exactly 1 unit more than degree of bottom, then you have an oblique asymptote. So you have to find all the asymptotes, whether horizontal or vertical or oblique. And you also need to find the critical points. Once you find the critical points, you can draw the sign chart, like we did one example here a few minutes ago. Once you draw the sign chart, locate all the critical points in the order. Let's say if 2 of them, if you have 2 critical points, -2 and 3. So first -2, then 3. And then you have to determine sign of f prime. Where is it positive? Where is it negative? And that will determine where f will be increasing, where f will be decreasing. And it will also determine local max or max and mean. So like we said, if, for example, the function is increasing, then decreasing, local max. If it's decreasing, then increasing, local mean, and so on. So once you have your sign chart, then you can sketch the graph of the function. You know where the function is increasing, where it's decreasing, you know the asymptotes, and you know x and y intercepts, and you can sketch the graph. Well, we explained about the steps, and we did many examples. We did for polynomials, we did for rational functions, for trigonometric functions, for exponential functions, for logarithmic functions. For each type, we did at least one example. So you can refer to the lectures or lecture notes for that topic. Okay, guys, so that was a brief review for the whole course, Math 113. Thank you, guys, and see you on for the final exam day. So I'll send you another email for the reminder of the final exam and the exact timing. Okay, guys, so thank you and see you soon.